Hi, this is the fifth lesson in electricity, mainly focused on Edexcel, Cambridge, and International Baccalaureate syllabuses. The link for the first four lessons are given in the description of this video. Before watching this video, you can go through them. Right. So, during the fourth lesson, we learned how to identify series connection and parallel connection. One of the properties of the series connection, the same current will flow through all the components. Okay, by using that, we can find and we can show that the voltage across the components, those are connected in series, will be divided at the ratio of their resistance. That is called potential divider method. We can use this as a method when we are calculating certain unknown quantities such as voltage across a component, or if you want to find the current through a component, we can use the potential divider method. So what it says, the total voltage will be divided across the components in series connection only. The total voltage or the voltage applied totally across the components, those are connected in series, will be divided across the components at the ratio of their resistance. So I'll show that now how it is, how do we get that. Okay, so here three components, a resistor or heater, a bulb, and a motor are connected in series. So the same current I will flow through all these components. So this is the equivalent resistance of these three components. You know the meaning of equivalent resistance. I already told that in fourth lesson. Go through there. Right. So this is the current flow here also. So I know R is equal to R is the equivalent resistance. That will be equal to R1 plus R2 plus R3. Okay, so that's the equivalent resistor. So the current flow here is the same as the current flow here. So I know the current flow here could be given as I is equal to EMF over R, that is R1 plus R2 plus R3. So that's the current flow in the equivalent circuit, right? So that should be the current in this series connection also. So the voltage across the resistor V1 is given by V1 is equal to IR1. Instead of I can use EMF over R1 plus R2 plus R3 into R1. This I can write EMF times R1 over R1 plus R2 plus R3. Right? Same way I can say V2 is equal to IR2. Instead of I can substitute E over R1 plus R2 plus R3 into R2. That is EMF times R2 over R1 plus R2 plus R3. Same way, V3 I can show that. I am not showing again. So I can say that is IR3, and that could be shown as EMF into R3 over R1 plus R2 plus R3. So you can say EMF is the total voltage applied across all these three components. Those are connected in series, and that voltage is divided across the components R1, R2, and R3. You can see the total voltage into that resistance, the resistance of the component over total resistance. That is the voltage across this component. Voltage across the bulb is equal to the total voltage into that resistance over total resistance. R1 plus R2 plus R3 is the total resistance or the equivalent resistance. Same way V3 is equal to the applied voltage into R3, that resistance over total resistance. So it looks like V1 is to V2 is to V3. If you find, you will see that will be R1 is to R2 is to R3. Is it? So that means I can say the total voltage is divided across the components. Those are connected in series according to the ratio of their resistance. Okay, we can use this in calculations, and we are going to start some calculations related to circuits. Okay, so it's a simple question, right? Three components are connected in series and their resistance are given. The EMF is 16 volt. The first question, find the voltage across the bulb. So simply I can use the potential divider method because I know they are connected in series. How do I know? There are no junction or branch between any two components. There are no junction or branch between any two components. So that means they are connected in series, so the same current will flow. So during series connection, the total voltage, that is 16 volt, will be divided across them at the ratio of their resistance, right? So first part I can use voltage across the bulb is equal to the total applied voltage into resistance of the bulb divided by the total resistance, 10 plus 20 plus 15. So if you solve it, you will get the voltage across the bulb. So that will be 3.56 volt. Second part, simple question, right? Find the current through the motor. So current through the motor should be same as current through the bulb. So I don't need to find the voltage across the motor now. I know the same current will flow, and I know the voltage across the bulb. So I'll find the current through the bulb. So I can use E equal IR for the bulb. Because series connection, the same current will flow through all the components. So I know the voltage across it 3.56. Current through the bulb is I, that will be the current through the motor, and same current will flow through the resistor also. So the resistance of the bulb is 10. So current will be 3.56 divided by 10, 0.356 amperes. So that will be the current through the, so current through the motor, that also the same 0.356 ampere. Okay, so here the second question. A motor and a bulb are connected in series, and the current flow through the circuit, or current flow through motor and bulb, is 1.2 ampere. The question is find the resistance of the motor, but the resistance of the bulb is given. So we can do it in two different ways. The first one, I can say the equivalent resistance. The equivalent resistance R0 is equal to R plus 10 ohm, because they are connected in series. How do I know they are connected in series? There are no junction or branch between the components, is it? So they are connected in series. Right. So I know that the current flow I is equal to the total voltage 20 over the total resistance R0. Or I can say V equal IR. For the equivalent resistance, I can say. So the current flow is given 1.2. The voltage is 20 over R0. I can say R plus 10. Solve it, you will get the answer. R plus 10 is equal to 20 over 1.2. Find the R. That is the resistance of the motor. This is the first method. There's one more method I can do, but this is the first method. So that will be 6.67 ohms. Okay, so second method, I can use a potential divider method also. So I need to find the voltage across the bulb. So I know the current, I know the resistance of the bulb, let it be V1. So I can say the voltage across the bulb, V1 is equal to IR. So the current is 1.2 into resistance is 10 ohm, so 12 volt. So that's the voltage across the bulb. Now use the potential divider method. That means the voltage will be divided across the motor and the bulb at the ratio of their resistance. I know the resistance of the bulb 10 ohm and the voltage across it. I found it now. So I can say use the potential divider. Shortly, right? Potential divider method. If I use the voltage across the bulb, that is 12 volt, 12 is equal to the total applied voltage 20 tau, 20 into the resistance of the bulb, that is 10 over the total resistance 10 plus R. Okay, so that's the potential divider method I'm using, and using for the voltage of the bulb. So applied voltage is total voltage is 20. The voltage across the bulb is 12. So 20 is the total applied total voltage into the resistance of the bulb divided by the total resistance 10 plus R. So solve it, you will get 10 plus R is equal to 200 over 10 into 20, 200 over 12. Find the R. That also 6.67 ohms. Same answer, you will get it. Okay, so this is the third question. There are two bulbs. They are connected in parallel. How do I know they are connected in parallel? You can see, I explained that in fourth lesson also. You can see that they are directly connected across two junctions. I can name them X and Y. So the bulb V1 and V2 are directly connected across the two junctions X and Y. So they are in parallel. That's the way we should identify. If the two components are directly connected across two junctions, then they will be in parallel among them. And you know the voltage across V1 will be same as the voltage across the junction. Voltage across the V2 also will be same as the voltage across the junction. Okay. So here the current through the bulb V1 is given 0.6 amperes. So the first question, the resistance are given V1 10 ohms and V2 15 ohms, but the EMF is not given. The question, find the current through the bulb V2. So current through the V1 is given 6 amperes. Question is, find the current through the bulb V2. I can name it I2. I2 is the current through the bulb V2. How can I find it? I can find the voltage across the bulb, that is same as the voltage across XY. So I can say for the bulb V1 use V equal IR. The voltage across the bulb is same as voltage across the junction VXY. I can call VXY because the voltage across the bulb is same as the voltage across the junction, because the connecting wires have no resistance, so there won't be any voltage across 2 points of the wire. That will be 0. So Vxy is equal to, current is 0.6 times the resistance 10 ohms, that will be 10 volt. So voltage across B2 also the same voltage, because voltage across B2 also the voltage across the junction. So I can say for bulb B2, I can use Vxy because voltage across B2 also the same as voltage across the junction is equal to I2 times the resistance of it is 15. So Vxy I found it, 6 is equal to I2 into 15. Find the I2. So that will be 0.4 amperes. That's the answer for the first part. Second part, find the current through the cell. So current through the cell, if I say that is I, the current through the cell is I. According to Kirchhoff's first law, the current I will split into 0.6 and I2. According to Kirchhoff's first law. So I can answer the second part. I is equal to 0.6 plus I2. That is 0.6 plus I2, I found it, 0.4. So current through the cell is equal to 1 ampere. Okay, so third part, find the total resistance of the circuit. That means that's the equivalent resistance. So they are connected in parallel. So I can directly use the equation 1 over R equal 1 over R1 plus 1 over R2. So 1 over R is 10 plus 1 over 15. Solve it and find the R, that is the equivalent resistance. So R will be 6 ohms. Okay, so this is method 1. I can name this as a method 1. Okay, so what could be the method 2? I can do the same question, the third part, by using some other method. Okay, another method I can do that. So the volt, I can imagine the equivalent resistance of these parallel connection as R. I need to find that R, is it? So I can imagine this circuit again like this way. This is the junction X. There is an equivalent resistance that I need to find it. This is the Y. I need to find this resistance R. Method 2 I am doing it, third part. So the current through the equivalent resistance should be same as this current. We know that is 1 ampere. That is 1 ampere. The voltage across the junction is the voltage across the cell also. You can see that voltage across the junction will be same as the EMF because there is no resistance for the connecting wire. So voltage across the junction, we found it in the first part, that is 6 volt. that is the voltage across the bulb, is same as voltage across the junction, that is 6 volt, same as the voltage across the cell. So this is 6 volt. Okay, so I need to use V equal IR for the equivalent resistance. I know the voltage across the resistance, that is 6. I know the current through the equivalent resistance, 1 ampere into R. So R is equal to 6 ohms. So same answer I will get it if I use the idea of equivalent resistance also. Okay, so this is the fourth question. 3 different components: a resistor of 6 ohms, uh, a motor of resistance 15 ohms, and a bulb resistance R are connected like this. Okay, now we'll analyze again. Last lesson also I analyzed it. Again I'll analyze it. How are they connected? The motor and this resistance, how are they connected? They are not in series, not in parallel. The reason, uh, between these two components, the resistor and the motor, there's a junction and a branch. Therefore, they are not in series. So, are they connected in parallel? No, because the motor is directly connected across the junctions. You can identify two junctions here. I can name them X and Y. Okay, so the motor is directly connected across the junctions, the two junctions X and Y, but the resistor, this one, is connected to junction Y, but the other terminal is not connected to the junction X. Therefore, these two are not in parallel also. Same if you think about this and this, they are not connected in series and not connected in parallel. If you think about these two components, the motor and the bulb, they are connected in parallel. The reason, the motor, the two terminals are directly connected to the junctions X and Y. For the bulb also, the two terminals are directly connected to the junctions X and Y. So the motor and the bulb are connected in parallel. Therefore, the voltage across the motor will be same as the voltage across the bulb. So this is the first junction. The current 0.8 ampere, which is approaching the junction X, will divide or split according to Kirchhoff's first law as I1 through this one, that is I1 through the motor, and I2 through the bulb. So I1 plus I2 will be equal to 0.8 ampere. Then here also again they will rejoin this I1, I2, they'll rejoin again and flow through the 6 ohm resistor. So current through the 6 ohm resistor will be equal to I1 plus I2, which is 0.8 ampere. So I can mark the 0.8 ampere here also. Right. First part, find the voltage across the motor. So voltage across the motor, how can I find it? So we know that the voltage across the resistor, I can find it. I can find the voltage across the resistor. Now these two are in parallel, right? These two are in parallel among them, and we can find the equivalent resistance, but I am not going to find it. So I can imagine the same circuit. I'm going to redraw this circuit again, little complicated because you know these two are in parallel. So if I can find the equivalent resistance of 15 ohms and R must be connected across the junction. That's a rule says, is it? When components are connected in parallel, and if you find the equivalent resistance, that equivalent resistance must be connected across the junction. Please go through the lesson 4, the fourth lesson. There, everything I explained already. So I can redraw this circuit again like this. This is 6 ohm resistor. This is the junction X. This is the junction Y. So equivalent resistance of these two, they are in parallel. I already explained it. That must be connected across the junction X and Y. So that I can call R0. R0 is the equivalent resistance of the 15 ohms and R. Right. Now look at here. This is the current flow 0.8 amperes. The same current will flow through R0 and come back to this one 0.8 amperes. This is 12 volt. Now you can see that the 6 ohm resistor and R naught, between them there are no junction or branches. So the equivalent resistance of these two and the 6 ohm are in series. They are in series, is it? So voltage across this one plus voltage across this one must be equal to 12 according to Kirchhoff's second law. In a closed circuit like this, I converted this circuit, I redraw this circuit like this. So the only difference is the equivalent resistance of 15 ohms and R is replaced by R naught, and that is connected across the junction XY. So after I connect it, now you can see that there are no junction or branch between 6 ohm and the equivalent resistance of these two R naught. There are no junction or branches. Therefore, 6 ohm and R naught, they are in series, right? So if they are in series, the same current will flow, the 0.8 ampere which is coming out of the power supply will flow through both R naught and 0.8 ampere. According to Kirchhoff's second law, the addition of the voltage across this and this must be equal to 12. The voltage across R naught, if I say V1 or V naught, and if I say this voltage is V1, V1 plus V naught is equal to 12 volt. So I can say V1 plus V naught is equal to 12 volt. V1, I know that IR, so current is 0.8 into 6 plus V naught is equal to 12 volt. Find the V naught. That's the voltage across the equivalent resistance. That is the voltage across the junction XY. That is the voltage across the junction XY. That means that's the voltage across the motor. Okay, so find the V naught here. That will be 7.2 volt. So voltage across the junction is 7.2. That's the V naught I named it. That's the voltage across the junction. So voltage across the junction is 7.2. But the motor is connected directly across the junction. Therefore, first part I can say voltage across the motor is also the same. That's the voltage across the junction. Also, I already told that the bulb also directly connected across the junction. So voltage across the bulb also the same 7.2 volt because they are connected in parallel among them. Okay, so second part, find the current I1. So that is easy. Now I know the voltage across the motor, so I can use V equal IR for the motor. V equal IR for the motor. So I know the voltage across the motor, that is 7.2. I need to find the current through the motor I1. Resistance of the motor 15. Find I1. That's the current through the motor. So that will be 0.48 amperes. Okay, third part, find the resistance R of the bulb. So third part, I'll do it here. Find the resistance R of the bulb. So I know that according to Kirchhoff's first law, 0.8 equal I1 plus I2. So that means I1 plus I2 is equal to 0.8. According to Kirchhoff's first law, I know I1 is equal to 0.48. So find the current I2 first. So current I2 will be 0.8 minus 0.48. That will be 0.32 amperes. Now use V equal IR for the bulb. So I know the voltage across the bulb, that will be same as the voltage across the motor, that is the voltage across the junction because they are connected in parallel. So that will be 7.2 equal current through the bulb is 0.32 into R. So R will be 22.5 ohms. Okay, this is the fifth question. Here a resistor 10 ohms and a bulb B2 are connected in parallel. The reason is you can see that the resistor 10 ohms and the bulb B2 are directly connected across the two junctions X and Y. These are the junctions I can call X. This is Y. So they are directly connected across the junctions X and Y, right? So if I find the equivalent resistance, with that equivalent resistance must be connected across the junction XY. I mentioned that in the lesson 4. So the equivalent resistance must be connected at the junction XY. With that equivalent resistance, the bulb B1 is in series. Okay. So find the current through the bulb B2. That's the question. So I know the current through the 10 ohm resistor is given 0.5 ampere. So voltage across the 10 ohm resistor will be same as the voltage across the junction. That will be the voltage across the bulb B2 also. So first part I can use V equal IR for 10 ohm resistor. So Vxy, the voltage across the 10 ohm resistor is Vxy, that is equal to 0.5 times 10, that is 5 volt. So voltage across the bulb B2 also the same because it's connected parallel to 10 ohm resistor. So now I can say for B2, I'm going to use V equal IR. The voltage will be same as Vxy, the junction voltage. So phi is equal to current through the bulb B2, I can say I2. So I2 into 6. So I2 will be 6 divided by, 5 divided by 6. That will be that will be 0.83 amperes. That's the first part answer. Second part, find the resistance R, that is the bulb B1, resistance of the bulb B1. Okay, so here also for this one I can find the resistance R in two different methods, right? First method, I'm going to find the current through the bulb B1. That will be according to Kirchhoff's first law. Current through the bulb B1, if I say that is I1 is equal to 0.5 plus I2. So I can find the current I1 flowing through the bulb B1. You know, this whole set, this combination is in series with the bulb B1. So I know the voltage across the junction XY, that I found it already 5 volt. So the voltage across the bulb, if I say V1, that voltage plus the voltage across the junction will be 9 volt. Is it? So I can redraw this diagram again like this. Second part, I can redraw it like this, 9 volt. This is bulb V1. If I find the equivalent of these two, I am not going to find it, but if I find the equivalent of these two, R0 will be across junction XY and will be connected like this. The voltage of the junction XY, I know that 5 volt. This is 5 volt. So the bulb B1 and the equivalent resistance of B210, that is R0, they are in series because there is no junction or branch between B1 and the equivalent resistance. So if I say this voltage V1, I can say V1 plus 5 according to Kirchhoff's second law in this closed circuit. V1 plus 5 is equal to 9. So V1 will be equal to 4 volt. That's the voltage across the bulb B1. The question is find the resistance R of the B1. So I can use V equal IR for the B1. Voltage across the bulb B1 is V1, that is 4 volt. Current through the bulb B1 is 0. That should be the addition of 0.5 plus current I2. So we found the current I2 already 0.83. So that current will be addition of 0.5 plus 0.83. That's the current through the bulb B1, because according to Kirchhoff's first law, I1 is equal to 0.5 plus I2. I2 is 0.83. So I can find the resistance R. Find the R here. R will be 4 divided by sum of these currents. That will be 3 ohms. Okay, so the same part, second part, I can do second method by using potential divider. So I'll find the equivalent resistance of 10 ohm and 6 ohm. So 1 over R naught, 1 over R naught is equal to 1 over 10 plus 1 over 6. Find the R naught. That will be 3.75 ohms. Now that R naught and R are in series, and we know the voltage across R naught, that is the voltage across the junction. We already found it, that is 5 volt. Is it? That is 5 volt. So this component, the equivalent resistance and bulb are in series. I can use the potential divider method to find the resistance R. So a little longer method, I can say potential divider method. If I use the voltage across R naught, the voltage across R naught, that is the equivalent resistance is 5. So 5 equal total voltage 9 into that resistance R naught, that is 3.75 over R plus 3.75. Solve it and find the R here. So I can say R plus 3.75 equal 9 into 3.75 over 5. Find the R. That will be 3 volt. Sorry, 3 ohms. Okay, so in this question, a resistor of 20 ohms, bulb 20 ohms B1, bulb B2, resistance unknown R. First part, find the resistance R of the bulb B2. So first part we can do it in two different ways, right? So method 1 for the first part, method 1. Okay, so if I say the equivalent resistors, I can identify two junctions here, X and Y. So the bulb B2 and B1 are connected to the same junctions, X and Y directly connected. So they are in parallel. And if I say their equivalent resistances are not, I can redraw the same diagram. The circuit could be drawn again like this. This is R naught, 20 ohms, the current 0.5 ampere, and this is 16 volt. Now you can see the R naught, that is the equivalent resistance of B1 and B2, is taken as R naught. That R naught and the 20 ohms are in series. So the voltage, the total voltage applied will be divided across them at the ratio of their resistance. By using that, I can find the R naught. So I know the voltage across this one I can find. If I say the voltage across 20 ohm is V1, I can say V1 is equal to IR. So 0.5 into R, 20 ohms. So that will be 10 volt. So I can use the potential divider method to find the R naught. How can I use it? This is 16 volt. That's the total voltage applied. These two are in series. There are no junction or branch, so they are in series connection. So I can say the 10 volt across 20 ohm is equal to the total applied voltage into, I wrote this 10 volt for this resistance. So that resistance 20 over 20 plus R naught. Find R naught. So cross multiply 20 plus R naught equals 16 into 20 over 10. From this, find R naught. So R naught will be 12 ohms. So I know R naught is the equivalent of this bulb, 20 ohms and R. So I know that 1 over R naught is equal to 1 over 20 plus 1 over R. R is the question. So 1 over 12 equal to 1 over 20 plus 1 over R. Solve it and find the R. So R will be 30 ohms. That's the answer for the first part. So second method, same diagram I'm using. The same diagram means the equivalent resistance of these two. I took it as R naught. Right, so the current flow is 0.5. So I can find the V1, that's the voltage across 20 ohm resistor. I can find V1 is equal to current 0.5 times 20, that will be 10 volt. So voltage across the junction, these two are in series, is it? Those two are in series. So voltage across the junction Vxy plus V1 according to Kirchhoff's second law. I'm using the Kirchhoff's second law. So Vxy plus V1 is equal to 16. So Vxy plus 10 equals 16. So Vxy equals 6 volt. So I know the voltage across the junction, right? I can say the current through the bulb B1 is I1. So I can find the I1 by using V equal IR for the bulb B1. This is little longer method, right? I can use V equal IR for the bulb B1 if I use it. I know the voltage across the bulb B1 is same as the voltage across the junction that I found it already, 6 volt. So 6 equal I1 times 20. Find the I1, the current through the B1. So that will be 0.3 amperes. I can find the current I2 now by using Kirchhoff's first law. I1 plus I2 equal to 0.5. So 0.3 plus I2 equal to 0.5. So I2 will be 0.2 amperes. The previous method I did not use the current, is it? I used potential divider method. So in this method I'm using the current, little longer method. So I2 will be 0.2 ampere. That's the current through the bulb B2. The voltage across the bulb B2 is same as the voltage across the junction XY. So I can use V equal IR for the bulb B2. So the V for the bulb B2 will be Vxy. That we already found it. That is 6 volt. So 6 equal, I can call Vxy for the bulb B2. 6 equal, current through that is 0.2 amperes into R. Find the R. That will be 30 ohms. So we'll get the same answer as earlier. So second part, find the power generated by the cell. That is nothing, simple. We can say P equal EMF times I. EMF we know 16 volt into current 0.5 ampere. So that will be 8 watts. Okay, so the eighth question, something related to explaining type question. So here B1, B2 and B3 are three identical bulbs. What do you mean by identical bulbs? They have the same internal resistance and they will give the same brightness when the same voltage is applied, right? So they have same resistance, right? So B1, B2 and B3 are identical bulbs. What will happen to the brightness of B1 and B2 when the switch S is closed? You can see that the B2 and B3 are connected in parallel, but the switch is open. But when the switch is closed, what will happen? B2 and B3 will become parallel to each other because there are two junctions. You can identify the junctions X and Y. But initially the switch is open means the bulb B3 is not part of the circuit. No chance for the current to flow through B3 because switch is open. So the current which is coming out of the power supply will just flow through B1 and B2 when the switch S is open. Okay, so since they are identical, they have same resistance R, this also R, but not functioning initially because switch is open. So initially both bulbs B1 and B2 have the same resistance. They are in series because switch S is open means this branch there won't be any current flow. I can imagine this is not there, is it? Since switch is open, so the current will flow just only through B1 and B2. So they will have the same current across them, through them, and same voltage. When you are comparing the brightness, very important, when you are comparing the brightness of two bulbs, you must compare their power, not the voltage, not the current. The power must be compared. The bulb with larger power will be the brightest. Or when you think about two bulbs, if they have same power across them, they will have the same brightness. Okay, so the brightness, when you are comparing, you must compare the power across them, not the voltage, just not the voltage, just not the current. Power across them must be compared. Bulb with larger power will be the brightest. So here you know that there is no current flow through this because I removed the circuit. But anyway, even if the wire is there, the switch is open, no current through B3. So B3 is not part of the circuit initially. So B1 and B2 are in series, is it? So they are identical. So they will have the same current through them. They will have the same voltage because EMF will be divided equally across them. So they will have the same power, P equal VI if you think. They will have the same power, so they will have the same brightness initially when switch S is open. Now they are closing the switches. What is going to happen to the brightness of B1 and B2? That's a question. Okay, now look at it. When you close the switch S, what's going to happen? B1, 2 and B3 are going to be parallel among them. So I'll close the switch, right? Now B2 and B3 are parallel to each other. They each of them have the same resistance R and R. Now what's going to happen now? So they are in parallel means the equivalent resistance of B2 and B3 will decrease. You know that I mentioned that in the lesson 3, yeah, in third lesson, when components are connected in parallel, the equivalent resistance will become lower than the resistance of the components, right? So when they are connected, when the switch is closed, the equivalent resistance of B2 and B3 will become lower. So I can redraw this diagram like this. It's showing only the resistance. If I consider this is the bulb B1, right, that has resistance R. So the resistance of B2 and B3, I draw only the resistance. So even for B1, I draw only the resistance. I told that I am not going to consider their function. So this resistance is R, which is the bulb B1. I am drawing the equivalent resistance of the circuit, equivalent resistance. So this is the equivalent resistance of B2 and B3. So they have same resistance. So 1 over R naught equal 1 over R plus 1 over R. R naught will be R by 2. So this is going to be R by 2 is the equivalent resistance of the bulbs B2 and B3. Okay, so now what will happen? The same applied voltage, the voltage is the same now. No change in the applied voltage, but the resistance, equivalent resistance of these two bulbs have dropped to R by 2. So the same applied voltage is going to be divided across B1 and the equivalent of B2, B3, that is across the junction at the ratio of their resistance. Earlier, when the switch was open, the EMF was divided equally as half EMF, or EMF by 2 and EMF by 2 here. Equally the voltage divided earlier. Now when the switch is closed, what's happening? The resistance, the equivalent resistance across the junction has dropped to R by 2. This resistance is remaining same. So when you think about the ratio, the potential divider method, this will be divided across these two according to the ratio of their resistance. So the voltage across this one will be larger than the voltage across this one. Now the voltage across this one is dropping. The reason the voltage across this one is increasing means voltage across the junction XY must drop, because this voltage plus this voltage is same as earlier. This is getting more now because this resistance is dropping, means this is getting more. So this is getting more means this voltage should become lower now. Understand? So what will happen? The current through the circuit will increase now. So the power of the V1 will increase. The voltage across it is increasing. Current through that also increasing. So the power of the V1 will increase according to P equal VI. Power of the V1 will increase. So if the power of the B1 increases, that means the brightness of B1 will increase. So compared to earlier when the switch was open, compared to that brightness of B1, now the brightness will increase. What will happen to the bulb B2? The voltage across the B2 is the voltage across the junction XY. The voltage across the junction XY is dropping compared to earlier. It was earlier half of EMF, now it's dropping further. So the voltage across that is dropping. The resistance of the B2 remaining same as R. Is it? Resistance of the B2 is remaining same as R. So if you think about power equal V squared over R for the bulb B2, if you use it, the voltage across the B2 is dropping now. The resistance of the B2 is remaining the same. So power to the bulb B2 will decrease. So the brightness of B2 will decrease. Here, the brightness of B1 will increase. I can say in terms of resistance also, the voltage across B1 is increasing. So voltage across B1 is increasing. Resistance of B1 is remaining the same. So brightness of B1 will increase. What will happen to the B2? The voltage across B2 is dropping because equivalent resistance is dropping across the junction XY. It has become R by 2, so the voltage across the junction will decrease. When the voltage across the junction decreases, resistance of the bulb B2 remaining the same, so power across the B2 is dropping. Brightness will decrease for B2, brightness will increase for B1. Okay, so that's the answer. B1 will have larger brightness or more brightness than earlier, but the brightness of B2 will drop compared to earlier when the switch was open. Okay, so I hope that you understood. That is the end of lesson 5. In next lesson, lesson 6, I will do about real cells and ideal cells. Ideal cells means they have no internal resistance. So far, the cells I used, I did not show any internal resistance. So, but real cells, that's a practical cells, actual cell we are using, they have internal resistance. So the terminal voltage will be lower than the EMF. So we will learn about that in next lesson, lesson 6. Okay, right? Bye.